What specific problem does the new method or algorithm aim to solve?
The new method, low-rank adaptation, LoRA, aims to solve the problem of reducing the memory footprint and computational resources required for fine-tuning large language models, LLMs, with billions of parameters. By freezing a pre-trained LLM and only training a small number of additional parameters, adapters, that are low-rank perturbations to selected weight matrices, LoRA aims to provide a more memory-efficient and sample-efficient alternative to full fine-tuning. The method seeks to approximate the accuracy of full fine-tuning on challenging target domains, such as code and math, while also acting as a regularizer to mitigate forgetting of the source domain. LoRA aims to strike a balance between learning on the new target domain and retaining knowledge from the source domain, ultimately providing a more efficient way to adapt pre-trained LLMs to specific tasks without compromising performance.
How does the proposed method or algorithm work, and illustrate it step by step?
The proposed method, low-rank adaptation, LoRA, works by freezing a pre-trained weight matrix W_text pre-trained in R(d) times k and learning only a low-rank perturbation to it, denoted as delta. The user selects which W_text pre-trained to adapt, referred to as target modules, and the rank RD_k. By doing so, only D times R plus R times K parameters are trained instead of D times K, reducing memory and computational requirements. LoRA can be applied to different modules, such as attention matrices, MLP matrices, or all modules combined. The method aims to provide a form of regularization by constraining the fine-tuned model's behavior to remain close to the base model. To illustrate the working of LoRA step by step, 1. Choose the pre-trained weight matrix W_text pre-trained, and select the target modules to adapt. 2. Determine the rank R for the low-rank perturbation delta, ensuring RD_k to reduce the number of parameters trained. 3. Train the model by learning the low-rank perturbation delta to the selected target modules, while keeping the rest of the weights frozen. 4. Monitor the performance of the model on the target domain tasks, such as code or math, to evaluate the effectiveness of LoRA in approximating full fine-tuning accuracy. 5. Analyze the learning and forgetting trade-off to understand how LoRA maintains source domain performance while adapting to the target domain. 6. Compare the regularization properties of LoRA with traditional methods like weight decay and dropout to assess its effectiveness in maintaining model diversity and similarity to the base model. 7. Experiment with different hyperparameters, such as learning rates, target modules, and rank, to optimize the performance of LoRA for specific tasks. 8. Evaluate the model's performance on challenging benchmarks, such as human eval for code and GSM-8K for math, to determine the efficacy of LoRA compared to full fine-tuning. 9. Consider the sensitivity of LoRA to hyperparameters and the choice of target modules, emphasizing the importance of configuration for optimal performance. 10. Explore extensions and variations of LoRA to enhance memory efficiency and performance, such as QLORA, Vera, and DORA, to adapt the method to different scenarios and tasks.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the LoRA method include reducing the memory footprint and computational complexity during training by freezing a pre-trained large language model, LLM, and only training a small number of additional parameters, known as adapters. LoRA achieves this by learning low-rank perturbations to selected weight matrices, which results in training fewer parameters compared to full fine-tuning. This method acts as a form of regularization that helps constrain the behavior of the fine-tuned model to remain close to the base model, thus mitigating forgetting of the source domain. Additionally, LoRA provides stronger regularization compared to traditional methods like dropout and weight decay, maintaining the diversity of generated solutions. Practically, using LoRA can lead to better maintenance of source domain performance, especially in challenging domains like code and math. It can help close the gap in accuracy between LoRA and full fine-tuning on certain target domains, such as math, while requiring longer training. LoRa's sensitivity to hyperparameters, particularly learning rates and the choice of target modules, highlights the importance of careful configuration for optimal performance. Overall, LoRa offers a trade-off between learning and forgetting, where it can achieve comparable target domain performance to full fine-tuning with diminished forgetting, making it a valuable method for efficient and effective model adaptation in various domains.
How is the method validated or tested?
The method is validated or tested through a rigorous comparison between LoRa and full fine-tuning for Llama 2.7b, and in some cases 13b, models across two challenging target domains, code and mathematics. The study explores two training regimes within each domain, instruction fine-tuning and continued pre-training. The performance is evaluated using challenging coding and math benchmarks such as Human Eval and GSM-8K. Additionally, source domain forgetting performance is assessed on language understanding, world knowledge, and common sense reasoning tasks. The study finds that LoRa underperforms full fine-tuning in programming tasks, but closes more of the gap in math tasks, albeit requiring longer training. Despite the performance gap, LoRa better maintains source domain performance compared to full fine-tuning. The trade-off between performance on the target versus source domain is characterized, showing that LoRa and full fine-tuning form a similar learning-forgetting trade-off curve. The study also compares LoRa's regularization properties to classic regularization methods, such as dropout and weight decay, demonstrating that LoRa provides stronger regularization and helps maintain the diversity of generations. Additionally, the study performs a singular value decomposition analysis to understand why LoRa underperforms full fine-tuning, showing that full fine-tuning barely changes the spectrum of the base model's weight matrices, resulting in high rank perturbations. The study concludes by proposing best practices for training models with LoRa, highlighting the method's sensitivity to learning rates and the importance of choosing target modules and rank.
What results were achieved with this new method?
The results achieved with the new method, low-rank adaptation, LoRa, showed that LoRa underperformed full fine-tuning in programming tasks but closed more of the performance gap in math tasks. Specifically, in code tasks, LoRa substantially underperformed full fine-tuning, while in math tasks, LoRa closed more of the performance gap with longer training. Despite the performance differences, LoRa was found to forget less of the source domain compared to full fine-tuning, acting as a form of regularization. The study also revealed that LoRa provided stronger regularization compared to common techniques like dropout and weight decay, maintaining the diversity of generated solutions. Additionally, the research highlighted that LoRa's performance was highly sensitive to learning rates, target modules, and to a lesser extent rank. The study concluded that LoRa is more suitable for instruction fine-tuning, IFT, rather than continued pre-training, CPT, and recommended targeting all modules with a relatively low rank such as 16 for optimal performance.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the LoRa method include the fact that it underperforms full fine-tuning in programming and math tasks. It requires longer training to close the performance gap with full fine-tuning, and it is more sensitive to hyperparameters, particularly learning rates, target modules, and rank. Additionally, LoRa may not be as effective in scenarios where there is a significant domain shift between the pre-training data and the target domain, as seen in the code tasks. Furthermore, while LoRa provides regularization by maintaining source domain performance and diversity of generations, it may not always achieve the same level of target domain performance as full fine-tuning. Lastly, the method's effectiveness can vary depending on the specific dataset and evaluation benchmarks used, as well as the complexity of the target domain being considered.